So I want you to do this example. I'll get you started on it. So what we have is an anchored wall here, sand over clay, the water table right there, and these are the properties of the clay. We have a C prime, a phi prime, an SU over sigma prime I, and the sand, we have phi prime of 43 degrees. Of course, C prime is 0 for the sand. And here are our unit weights. So what I want is the active and passive stresses at T equals 0 plus. So, and notice this wall is built by excavation. So that means that I'm going to get you started on the solution. At T equals 0 minus, this is my situation. I've driven a sheet pile wall, for instance, into the ground, and the sand's on both sides. So then what happens? Then we put in the anchor and we excavate this side here. And okay, so that's my T equals 0 minus situation. That's my T equals 0 plus situation. And I want the stresses at T equals 0 plus. So the first thing you have to do is you have to get the undrained strength in the clay. To do that, you're going to use the T equals 0 minus figure. So in other words, you look at this figure, that's what determines the strengths, because that, sand has been, consolidating that clay for, 100,000 years or whatever. We're going to assume it's well consolidated. And so we're going to use the SU over sigma prime I of 0.62 to get the SU. So what you need to do is look at this figure to get the sigma prime I, use that 0.62 to get the SU. So that's what you're going to do there. And then once you have that, then I want you to use this table here. And I've filled in the sigma v's for you. I've given you the depths, 2, 6 minus, 6 plus, 12, and so I've calculated those for you. You should be able to do those. So pause the video here and fill this in, get our sigma h's. Get the sigma h is what we want to get for that. Okay, assuming you've done that, what do we need to do to find the answers? Well, I've got to compute the Ka in the sand. Tangent squared 45 minus phi prime over 2 comes out to be 0.189. In the clay, what's my sigma h? Well, it's at T equals 0 plus. That's what we asked for. So that means what? That means total, we're, in our Ed's tough, where are we? We're here. Total undrained fast. I use total stresses. So in other words, it's a total stress analysis, and so I'm using those total stresses. So we are total undrained fast. And so in the clay, in the sand, we're always effective drain slow. So, okay, so how do I get my I use my T equals 0 minus figure, so I'm looking at this figure. At a depth of 6, it's 600. Why? Because the sand is 100 and it's dry. So 600 at depth of 6, and at 12 I get 600 plus 6 times 110 minus 6 times 9.8 gives me, 885.6. Then what do? I take my SU over sigma prime I, I put it in there, and multiply those out. Here are my values of SU for those two depths. So at 6, the SU is 372. At 12, the SU is 549. All right, so then when I go into my table, this is the sand here, sigma V I gave you. It's dry, so sigma V prime is the same as sigma V. And then how do I get my sigma H prime? Well, 0.189 times the sigma V prime gives me my sigma H primes. So that's easy enough. And then my sigma H, I just add the pore pressure, which is 0. So sigma H prime and sigma H are the same. In the clay, I'm using these equations. So in the clay here, I'm using those equations. So what? I don't need any of this because everything is total stresses. Like I say, we're doing our total stress analysis. So using these equations, then I take 600. Well, you can see it. We're in the active zone, so it's 600 minus 2SU. So it's going to be 600 minus 2 times the 372. And then it's the 1260 minus 2 times the 549. So these go in here like that. And now, what do I end up with? Well, sometimes you end up with a number that's below 0. Well, we don't like that, so we're going to use 0. Okay, because when you actually end up doing your final analysis, we're not going to use negative numbers here for the sigmas. And for this other one, we get 162. So that is our active. So these are our active stresses. In the passive zone, I have 6 and 12. And now I'm going to use this expression. Sigma V, here's my 2 plus 2. And again, SU, SU. So those are my passives. All right. Let's look at the next example problem. And now it's the same problem. So in other words, here's what's interesting here is if I look at this to a certain extent, sand over clay, all the properties are the same. The end result is the same as this one. Same properties. Same end picture. In both cases, I have my, it's a 6-foot wall embedded another 6 feet. And so the end result is the same, but this time I'm going to build it by filling. So in other words, I'm going to help you out with this. Well, I'm going to do this one for you. So here, my t equals 0 minus picture is completely different. So in other words, before we started like this and excavated. Now we're starting like this and we're filling this soil in. So we're built by fill. We're going to get different results. Why? Because my undrained strength is going to be different. Why? Because I still use my t equals 0 minus figure to get the undrained strength, but now what? My t equals 0 minus figure looks like this. There's no sand there consolidating the clay. As a result, my sigma prime at 6 feet is 0. There's nothing here. And my sigma prime at 12 feet is pretty small. So the end result is I'm going to still use the 0.62 here to get my SU, 0.62 times the 285.6, I get only 177. So I end up with different strength. So this strength is 0 at the surface, and then I only have 177, whereas in the previous one I had 372 and 549. So my clay is naturally weaker because it hasn't been consolidated by the sand. The Ka in the sand doesn't change, and so all of my sand stresses are the same, so that doesn't change. But now I go, what? I've got my sigma V. So notice that when I get my sigma V, now I'm looking at the t equals 0 plus picture here. So, and so I have my sigma V minus 2SU. Well, SU is 0, so I get 600 there. And then I get sigma V minus 2SU here is 906. So, and in the passive side, I go, again, now I'm looking at my t equals 0 plus figure here again. I have 0 and 660 there. And so it's 0 plus 2SU. Well, that's 0. And sigma V plus 2SU. Well, I get 1014. So notice what's happened is I have 600, 906. Compare that to, well, negative 144, 162. So what do I see? It's much bigger. So I have larger active stresses. Now let's compare the passive. 0 and 1014 compared to 744, 1758. So what do I end up with? I end up with larger active and smaller passive. So what is my situation? Well, like I say, active is bad, passive is good, and we want a big passive, but we end up with a smaller number. So this is a much worse situation. And then at the same time, we want a small active, but this is a bigger number. So this is a much worse situation. And the end result is, even though the picture is the same, the picture of the end result is the same in both cases, because we built the wall differently, built by excavation, built by fill, we end up with completely different results. And it's all because of this, the strength of that clay is different when we start out. So that is why we have to remember how we build the wall, ultimately, to determine the stresses on the wall. Makes a difference. Okay, I'm going to talk about this. I'll do it in more detail a little bit later, but I want to say something about what we call braced walls. Now, what does that mean? Well, another way to support a wall is to brace it across. For instance, suppose I build a trench. So what we're looking at here is a plan view of a trench. So here's my trench. I haven't drawn it that long, but here's the plan view of my sheet pile wall installed in the ground. And then what we do is, since it's a trench, I can brace the wall. In some cases, you can just brace right across, and you don't have, there's no anchor involved. Now, again, we're going to look at the construction sequence of doing something like this. So, like I say, the construction will influence the stresses. As now, so this is an elevation view. We start out and we drive these sheet pile walls into our ground, and then what do? Then we start to excavate. So 1, we drive the sheet piles. 2, we excavate, and sheet piles tend to be a little bit flexible. So what happens is, as we excavate, the sheet piles bend in a little bit, and we can get, what amounts to be, active type stresses there. Then what do? Then we take and we brace across, and then what's the next step after that? Once we've braced across, then we want to excavate some more, so we go down deeper. Well, when we go down deeper, this is braced, but then the wall deforms because this is a flexible wall, and we end up with sort of active pressures here. And then what happens is as this moves in here, it wants to bring this soil with it, but this wall is now not moving anymore. So you start to get sort of not fully passive, but what I'll call semi-passive stresses up there. And so we're starting to get higher stresses in this region than active. And put it this way, you can keep going, add more braces, excavate some more, depending on how deep you're going and that sort of thing. But the end result is we get a strange pattern of stresses on this particular wall. And what that means is that the earth pressures are not simple, active and passive anymore. And people have, measured the stresses on these walls under these situations, and this is what is this is what people use. Odd looking. So this is my end result. There's my wall, and in a sense, there's my. That's just the part of the wall that you can see. We have our excavation here. It looks like that. We've braced across, perhaps like that. And instead of using our regular active and passive, people say, okay, we're going to get this trapezoid. It looks like that. It's not going to be a triangle. Normally we'd have what? We'd have something that looks like that. Well, we don't have that. Or actually, maybe it'd be more like that. We don't have that. We have, looks like this. And this is for sand and clay drained, approximately. And the shapes are here. If this is H, then that's 0.2H, 0.6H, 0.2H. And this is 0.8 gamma H Ka. So for clay undrained, then the shape is, again, a trapezoid instead of something that looks like that. And this is 0.25H, 0.75H, that's H. And then this is sigma V minus 2SU average. When I say at average, at about 0.25H depth, take the SU. So, again, how the wall is built affects the earth pressures. It's something that you need to keep in mind. Okay, we'll look more. And again, let's look at another wall here. Like I said previously, these big, massive gravity walls are not practical and are seldom built. So there are lots of different ways to build walls. I'm showing a few here. And so let's look at a soldier beam wall. What is that? Well, again, this is plan view. So suppose I've got an excavation here, maybe building a basement. And what I can do is I drive these H-piles. They're called H-piles, but they look like I-beams. They're eyes, These look like I's in this direction. They look like H's in that direction. So H-piles, I-beams, whatever you want to call them, they're about the same thing. And what you do is you drive these before you put in your excavation. So the excavation doesn't really exist yet. But this is where your excavation is going to be, and you surround that with driven H-piles. And then what happens is you as you begin to excavate, you use these. Here's my H-pile. There's an H-pile. And these H-piles, they act like beams. So that's really, sometimes it's called a soldier pile wall, sometimes a soldier beam wall. But in a sense, they're meant to resist bending. It's like I say, this is an I-beam. So that's where the beam comes from. It's like an I-beam. So what you do is, as you excavate, you put in some wood lagging. So just boards, basically. And these boards form the wall. And these piles are driven deep into the ground, well below the excavation. And they are used to hold the wall up with these boards here. So what we're doing here is we are inside. The view that I have over here is that we are standing inside the excavation, and we are looking at the wall as it is constructed. So this is what it looks like. You've probably seen, these are quite common, you've probably seen these. Now, how do we get the wood in there? So in other words, what happens is you excavate, and you take the wood lagging, and you have to cut it the right length so that it fits inside, and you can swing it in, jam it up in here and then swing it in so that it can pass through. But then it can't be too short. It's got to fit in here so that it fits within the between the two I-beams or H-pile. So that is a soldier beam wall, quite common. Tie-back walls, okay, so what happens, you have, again, you can have sheet piles, and you can drill through there and grout these. I think I've talked about these. A little bit of repetition here, so I'll apologize for that. But the idea is that you create many anchors, and rather than just one anchor. And because many anchors is usually better than one anchor, and you grout these using a form of cement. Generally, you can have rebar, and then you lock it off there, so you tie it there. And you test these, make sure they're solidly into the ground. And what happens is, as you go deeper and deeper, so you excavate a little bit, you put in a tie back. You excavate some more, you put in another tie back. Excavate some more, you put in another tie back. So as you go down, you add more and more tie backs into the ground. Holds up the wall. Okay. Let me continue just a little bit more. And we've also talked about this reinforced earth wall or mechanically stabilized earth wall, MSE wall, lots of different names. As I stated before, what we do is we have, we start making, well, we have, for instance, a ground surface that looks like this, and we want to create a wall here, and could keep going up. And the way to build that wall is a little bit at a time. So what you do is you put in some soil, you put in a concrete block, you put in reinforcement, put in some more soil, another concrete block, more reinforcement, etc., until you build it upward, and then you can end up with a good sized wall, and they behave very well. Now, what you've done by one way to look at these walls, and they're more complicated than this, but to make sure that it's at least completely stable, you have to, as a minimum, this block has got to be, this block here has got to be big enough gravity wall to be able to withstand a basic gravity wall analysis. And so in other words, this is my block of concrete in a sense, is the weight of this. It's got to be capable of withstanding that. I have active earth pressures here, and I have friction at the base. And so as a minimum, it's got to be able to handle that. Now, of course, this is not a rigid thing, and there's lots more involved with designing this in the sense that the blocks can pull out and that sort of thing. But for the time being, what you can do is you can think of this as basically a gravity wall, because that's what you're doing. You're trying to create a block of earth, a block of earth. And we talked about the case where, for instance, we have a higher water level on one side than the other, and we talked about the flow nets, and this is another review of that. We need to draw the flow net to get the pore pressure, and so you can pause the video and look at this as another example. And for instance, if I look at this flow net, what do I see? This flow net has 3 pipes, or 3 flow channels. There they are, 1, 2, 3. 3 flow paths, 3 flow channels, 3 flow pipes. And it has 7 squares. What does that mean? 1, 2, 3, 4, 5, 6, 7 squares per pipe. So 1, 2, 3, 4, 5, 6, 7. There's always 7 in each one. It doesn't matter which one you look at. 1, 2, 3, 4, 5, 6, 7. Again, so I have 7 squares in this particular one per pipe. So notice my total drop. So there's my head drop. Just to make the math easy, I set that as 7 meters. So if I have a total drop of 7 meters, then I have 7 squares. So 7 meters per 7 squares, that means I get 1 meter of drop per square. 1 meter drop in head per square. So if I'm looking at, say, my point of interest here is at point D, well, what does that mean? So to go to point D along the side of my wall, the water has gone through 1 square, 2 squares, 3 squares to get to point D. So I have 3 meters drop because I have 1 meter per square, 3 squares to get to point D. So that means 3 meters drop. So how do I measure that drop? If I put a piezometer at point D, well, it's going to give me the water levels. There it is. And what is it? It's dropped 3 meters. It doesn't, in other words, the piezometer doesn't go all the way. The water in the piezometer doesn't go all the way to the top, to the water table there. Instead, because of this effect of dropping 1 meter per square, it's there. So I have 3 meters drop. I then use this to determine the pore pressure. So U at the point of interest is H gamma W. Well, you have to look at the geometry. There's my H, is the distance between point D and 3 meters below the water table. So, you have to look at your geometry properly to get that. And so what we do is now, for a point of interest, basically everywhere the flow net touches the wall is a point of interest. Well, so point B, point C, point D, point E, I would use those. And then when I make my table here, what's my point of interest? A, B, C, D, and E on the active side. And then you're going to use the flow net to get the pore pressure. Everything else is the same. Everything else is the same as we normally do, but to get the pore pressure, we have to use the flow net. So everything else is the same. So as an example, I've gone through this where we're saying the soil is a silt, so we're saying the whole soil here is a silt for the sake of discussion. And here are our properties of our silt, C prime and phi prime. And this is our T equals infinity situation. And so if we're doing things at T equals infinity, what does that mean? Then we have to use our drained equations, right? So these are our drained equations. And for the sigma prime HA and sigma prime HP. So again, this is the same problem, so it's 7 meters and 7 squares, that's 1 meter per square. So, I look at each point according to this picture, and these are the depths of each of those points. I also look on the passive side. I can do the passive side as well. I haven't quite shown those points, but those are there. And so what does that mean? Well, with the numbers given, if I look at point D, that's the one that we were doing, right there, well, it's a depth of 10 meters. The water table is at 1 meter on this side. And so I know it goes 3 meters below the water table, so that's going to be I can't see it there, but it's 4 meters. So the height in the piezometer is at a depth of 4 meters. The water level in the piezometer is at a depth of 4 meters. D is at 10 meters. So the H is 6 meters. So H is 6 meters. So, you can do that calculation for either of these. So you should pause the video and make sure that in each, if I were to show each piezometer, those would be the depths in each piezometer. And that would give us the pore pressures here. On the passive side, again, I'm going to show you these, but I'm going to show you some of these, but we would do something similar on the passive side. Again, everything else is the same as we normally do. Here are a couple other points. Or here, this is for F. Point F is on this side over here. And if you look for point F, it's what? 1, 2, 3, 4. I go through 5. So it drops 5 meters from 5 meters below the water table here. And so that distance is 5 meters. Here's my water level in my piezometer at F, and it's dropped by 5 meters. And then I can use that to get my HF. So this is at 1. This is 5. So this is going to take me to 6. Point F is at 12. So point F is so what is that? That's 1. 5 takes me to 6. 12 minus 6, 6. So point F is 6 times 9.8. So I'm going to let you go through the rest of these. You can pause the video and figure out the values for all of those. So that's how in detail you can get those pore pressures from the flow net. Some other miscellaneous, we talked about it. We want to make sure that there's no trapped water behind the wall. It produces very high pressure, so we try to avoid this. We put in drainage holes, weep holes in the walls, make sure the wall is permeable so water can get out. And if we put in gravel here, it's going to simplify it's going to make it easier for the water to escape. So we can put gravel. We want to have something free draining next to the wall. And the end result is that if there's a water table there, the water table is going to be curved. It's going to go down like that so that we don't get high pressures up against that wall. I'm going to say something about, related to walls. We have slope stability, and I've said something about this in soil mechanics, but I'll repeat it very quickly here. So typical soil profile on a hillside is what? I have rock. The hill is there because there's rock there. But what happens is we usually accumulate a layer of soil on top of that rock, or frequently, it depends on a lot of different situations. And a lot of times what we're worried about is this soil sliding out. And when does that occur? Well, rain plays a big role in this, and in that rain will increase the likelihood of this thing sliding if it's embedded in the soil in that on that hillside. And well, if we think it through, if that soil is a gravel, then what happens? The water comes through, and it goes right through the gravel to the base, and it just rolls away. So it doesn't really accumulate. And if we'll take the other extreme. If it's a clay, if that soil is a clay, then what happens? Well, if it's clay is not very permeable. So we're talking about right after the rain. What happens is the water comes through on the clay. Well, it doesn't go down, it just rolls off the top. So if it's a gravel or a clay, if it's gravel, it goes to the bottom, goes down. If it's a clay, it goes onto the top and goes down. So it doesn't really cause a problem in a sense. But if we have sands and silts, then what happens? Well, then the water comes down, some of it rolls over the top. Some of it goes in, but it doesn't go all the way down to the bottom and goes down the hill quickly because sand and silt are not necessarily that permeable. So what happens is that the soil, in a sense, absorbs the water. And when it absorbs the water, then the water is sitting there. Well, what does water want to do? Water wants to go down the hill. And so if it sits there, and there's enough of it, and we start looking at the weight of our soil, because now the soil gets heavier, we have a shear. So this is this little block of soil here. There's a free body diagram of that block of soil, and you start looking at the weight. Well, the weight keeps going up, and what do we have resisting it? We have shear stresses at the base. And normal stress, so again, we're making a cut through soil, so we have normal and shear. And then we have, stresses here and stresses there, the soil next to it, so that's the stresses from those soils. And then basically we take the, in a sense, active and passive stresses. So, it's active, passive. What we do is we analyze this, and if the shear stress at the base is not significant enough to hold that back, then this will fail. And so, like I say, so our soils that we have to worry about are the sands and silts. Well, I will just note that with time, we never have a perfectly smooth slope. It really looks like this. And if we have clay here, just to let you know what happens, we get puddling here, and the water seeps in. And so clays over time will be bad also, generally. Because they will tend to absorb the water and not have it all just roll off simply because this is the way the real slope looks. So we have to watch out for clays also. But, the gravels are good because the water will run right through this, and the rain will not affect gravels. Or if we have a coarse sand, same thing. So, but fine sand, silts, and clays, we have to worry about these for just the effect of the rain. And that's why, especially at the end of the rainy season, what happens is that we can get a lot of slope failures in clay simply because they've become saturated with all the rains and puddles. So that you'll see these quite frequently along the side of the road, is that suppose I have a little roadside slope failure, and the soil goes into the road. Well, they clean it up, but then what do? They have this slope failure here. And if there's been a failure, then what? Then the factor of safety against sliding is 1, because we've just had a failure. So that means the factor of safety is 1. So what is frequently done? Oh, just put a bunch of large boulders there. Gravel, big gravel particles. In a sense, they've just solved the problem. So you'll see, if you're driving down the road, it's not going to be unusual for you to see a pile of boulders there. That acts as our gravel to stabilize those. All right, I'm going to stop there.